Okay, welcome everyone. To get started. So it's great to have Maria Alessandra Papa, and she will tell us about the next big gravitational wave discovery.
All right. Well, thank you very much for giving me the opportunity to tell you about gravitational wave research that you don't hear that much about a lot. I guess this is in the spirit of looking forward and seeing what's coming next. So since the topic is gravitational waves, I can't not have a slide reminding that gravitational waves are ripples of space-time traveling at the speed of light. They're transverse, and important, they're produced by varying mass quadrupoles. So gravitational waves are expected in a variety of circumstances to be emitted. And the only thing I really want you to take away from this slide is that they can, in principle, span a very broad frequency range, from really small frequencies to about a few kilohertz. And my talk is going to concentrate on this high end of the frequency range. There'll be also a talk, I guess, the day after tomorrow by Louis Lehner. And other talks that you're going to hear about are concerned with, results from gravitational wave sort of induced observations in this other lower frequency range. So, but for now, let's concentrate on the kilohertz region, okay? And why is that? Well, because there are detectors right now taking data and observing gravitational waves that have a significant energy content, these signals, in a frequency range that goes between, let's say, 20 to 30 hertz to about 2 kilohertz. This is this represents the noise of data from gravitational wave detectors. And so where the noise is lower, that's where we can measure signals better. And this is a function of frequency, and so this is why it's between about 20, 30 hertz to about 2 kilohertz. So these are data right now coming from the two LIGO detectors and the Virgo detectors. LIGO detectors are in the US. The Virgo detector is located in Europe, in Italy. All right. I guess you all know about the big result. That was the first gravitational wave signal that was detected on the 14th of September 2015. And it was a signal coming from the in-spiral of two black holes of about between 20 and 30 solar masses. And I put the references to two papers. This is the discovery paper, the PRL. And this is an interesting paper that talks about the basic physics of this event that I particularly like. Now, this event lasted not even a second, okay? And this is the super famous wave shape, at least it's famous in the gravitational wave community, that was detected consistently in the Hanford and the Livingston detectors. Big discovery, big announcement that happened in Washington a few months later, because the collaboration had to go through all the checks and validations. This is David Reitze, the spokesperson at the time, now LIGO Lab, that said, ladies and gentlemen, we did it. We detected gravitational waves. It was a very exciting moment. This is me, actually, with the rest of the LIGO, the announcement at the press conference. And then a little bit there came the big prize to the three sort of founding fathers of the project. And this was a party in Stockholm the night of the award of the prizes. All right, that was in 2001. This is down here. And we are now in 2004, so the fourth O for observing run. Okay, and what you see here is the average reach for for a neutron star in spirals. And you can see here, that's the reason why I put it up, that it's increasing. So the detectors are still being commissioned and the sensitivity is improving. It means that each observing runs, they can look further and further away. And you can also see that the reaches of these detectors, LIGO, Virgo, and Kaga in Japan, are somewhat different, representing different degrees of development. The number of detections has also dramatically increased, okay? And we are now up to about 180 events that have been announced. 04, the second part of 04 is ongoing, and these numbers are not public, but obviously the number of detections continues to increase. Now, the gravitational waves from these signals. I said gravitational waves are emitted by varying mass quadrupole, and the varying mass quadrupole comes from the orbital motion of the two bodies sort of around each other. And the thing that I'm going to, and that is, fractions of seconds or seconds, depending on the mass, before they merge. But what I'm going to talk to you about is a signal that's not being detected, that I think is going to be a really interesting one. That's the signal that I'm trying to detect. That comes from, instead, in its simplest form, a rotating neutron star. So the actual gravitational wave is emitted if the star has a varying quadrupole moment produced basically by deviation of the star from a perfect axisymmetric shape. So in the case, if we model the star as a triaxial ellipsoid, that means with an ellipticity, an important quantity is this measure of the deformation, where I here are the moment of inertia along the principal axis, okay? So the type of signal that we expect is basically a sinusoidal signal with a frequency of the gravitational waves at twice the rotation frequency, okay? And the thing is that as long as the star rotates and it's deformed, the signal is always there. So unlike these signals from the mergers that basically go off and last only a very short time, this signal is a continuous signal. Okay, so then the question is, what could generate such a deformation? Well, there's a number of reasons, and I don't want to spend a lot of time, but the stars, neutron stars, are born in messy events, supernova explosions and core collapse, and these are unlikely to be perfectly symmetric events. And so there could be some deformation that's frozen in from this messy birth event. We know that there are star quakes. We know this, we suspect this from observations of flares in neutron stars. And these could point to readjustments in the crust, okay? We know that in accreting systems, and these are particularly interesting, the accretion happens through hotspots funneled by the magnetic fields. And these are clearly points where there is an asymmetry in the system, okay? That could be temperature and density gradients that produce then this non-symmetric, axisymmetric shape. There's, of course, internal magnetic fields. Now, a lot of work from people who model neutron stars to try and model ways in which the star could be deformed. These are complicated and different and difficult simulations. And perhaps an easier question that people are trying to answer is, what is the maximum deformation that a star could sustain? And here the answer really depends on the composition, on the internal composition of the neutron star, because the answer to this question basically depends on the breaking strain of the crust. And the answer, depending on the models, ranges between several orders of magnitude. The smallest ellipticity, on the other side, comes from when one assumes that the deformation is due to a magnetic field that's not aligned with the spin axis. And unfortunately, the numbers here are pretty small, 10 to the minus 12, 10 to the minus 14. So from this, really, what I wanted for you to take away is that stars could be deformed, yes. You can't expect them to be perfectly symmetric. To what degree they're deformed, it's an uncertain quantity, okay? Sorry? We'll see that. No, it doesn't. It depends very much on the composition of the star, on the core as well. Yes. And that's why there's all this uncertainty. Now, suppose that we do see these continuous waves. Well, indirectly, for example, if we measured a really large ellipticity, the people who make these models, if I measured an ellipticity of 10 to the minus 3, then this would tell us that probably the inside of the neutron star would need to be pretty exotic. Although I must say that there's a number of degeneracies here. So there's a lot of caveats in going from measuring a continuous gravitational wave signal and actually, deducing something about the internal composition of the object. But certainly would be a probe, because the deformation is sourced. It's a large-scale deformation sourced by the structure inside, which is a place that we really know very little. We know that there's about probably 10 million neutron stars in our galaxy, of which, as pulsars, we only see a few thousand. Okay? So we know very little about the population of neutron stars of the galaxy, and perhaps gravitational waves could give us access, a window on a slice of that population that we do not see as pulsars. The signal is always there, and pretty much as for pulsars, pulsar timing and pulsar observations have allowed very precise tests of GR. With gravitational waves, we would be able to do the same sort of precise testing, but with a completely different probe. Now, if we could have electromagnetic timings in conjunction with a gravitational wave observation, this means we could measure the spin frequency of the object, and we would have the gravitational wave frequency. And by comparing these two, we would understand what the emission mechanism is, because the relationship between the gravitational wave frequency and the spin frequency tells you what is the source of the gravitational wave emission. If it's at twice the rotation frequency, we would know that it's a quadrupular deformation. For example, if it was close to the rotation frequency, we would know that it could be due to a wobble. If it was for thirds of the rotation frequency, we know that it's R modes, so relativistic fluid mode oscillations in the star. Even more intriguing if the signal did not come from a neutron star. And I'll briefly mention something about this. Okay, so how strong are these signals? The signal that we receive obviously depends on the distance, and then here on the moment of inertia, this deformation, and the square of the frequencies. And so if we plug in some numbers, and here I plugged a deformation of 10 to the minus 6, a gravitational wave signal at kilohertz, and a distance of a kiloparsec, you get a few 10 to the minus 25, okay? And compare it with the typical amplitude of the signal that we detect from binary in spiraling signals, which is at the level of 10 to the minus 21. So here, we're basically orders of magnitude lower, okay? So how is it possible that I can even dream of detecting this? Well, you know this actually, because if you have a sinusoidal signal, you know that you can basically pull it out of the noise by integration, right? You observe, you compute an FFT over a long observation time, and then you take the power, and you know the longer the observation time, the clearer would be the peak at the frequency of the object. This is basically the concept, although when we actually compute the proper optimal detection statistic for a continuous wave signal, it is slightly more complicated. I don't have time, I don't think it's very useful to illustrate all of this. So what I want, though, you to take from this is that the signal here that I have out of the detector is a superposition of the two polarization wave shapes. These are sines and cosines, basically. Each sort of filtered through what the detector sees given at any given time, given the relative orientation between the detector and the source, okay? And the thing is that you can reparameterize the signal in a way that then makes it easy to analytically maximize over part of the parameters of the signals. The signal has basically two sets of parameters, so-called amplitude parameters and phase parameters. And you can analytically maximize over the amplitude parameter the log likelihood ratio, okay? So basically our coherent detection statistic is analytically maximized over the amplitude parameters log likelihood ratio. Test the hypothesis, is the data more consistent with a signal with these parameters or with Gaussian noise? I'm going to come to that exactly. Yeah. Mm-hmm. You mean an actual, well, we can do it in software, which is a lot cheaper. Yes, people have also built them in torsional pendulum antennas. So that's a mechanical resonator that's to observe the crab in Japan many, many years ago. But that's not as sensitive as the interferometric broadband detectors that we have, and we can actually do the pointing in frequency evolution, okay, and sky position in software with this, and it's definitely more practical. So basically, you have this black box, and if you want to, you can actually download the open data of LIGO, use this routine that it's in the LAL Suite software library, and check your favorite pulsars. So here are the pulsars. These are the known pulsars as a function of their spin period and spin period derivatives that we know of. And in yellow here, I have highlighted the high sensitivity band of the detectors in frequency. So here I put a second axis that shows you the frequency. And so you see, as I was saying at the beginning, it goes from about 20 hertz to 2 kilohertz, okay? So there are a bunch of objects that fall into this band. And so these are routinely searched for. Unfortunately, there's no detection, there's been no detections, and so what we do is place upper limits. Upper limits means, as a function of signal frequency, we'll tell you, consistent with our null detection, since we know the sensitivity of the search, okay, we can say, you know, what is the largest gravitational wave signal, the smallest, largest gravitational wave signal that we can exclude, okay, since we haven't detected anything. And so you'll see a number of these plots. And where the upper limits are will tell you something about the sensitivity of our searches, and so also about the ellipticities that we could have detected. Before I proceed in showing you actually some results, I want to talk about an important benchmark, which is an indirect upper limit of gravitational wave emission. So these objects, we know that they spin, and we know that they spin down. So if they spin down, it means they're losing rotational kinetic energy. So we can ask ourselves, what would be the gravitational wave amplitude, okay, that would be supporting all the energy loss in gravitational waves, all the kinetic rotational energy loss that we do observe? How high would the signal need to be? And this is the formula. This is the gravitational wave amplitude that we would measure at a distance d from an object with that spin down and that frequency. This is a ratio actually that obviously doesn't depend on whether it's gravitational wave or spin frequency, right? But I indicated it here as the gravitational wave frequency. And if our upper limit is larger than this, well, what does it mean? Are we learning something? No, we're not. We're not, because we already know that the gravitational wave cannot be, the amplitude cannot be higher than this number. If our constraints are even higher, we're not learning anything, okay? Sorry? Yeah, but the electromagnetic observers time these objects very regularly. And so when we do the search, we know exactly what waveform we're targeting. And so these are results out in 2022 from the LIGO-Virgo collaboration. And here you see are these upper limits. As a function of frequency, you have the maximum sort of gravitational wave strain, the minimum, the smallest signal that we can exclude because we didn't detect anything. And these are the results are actually the stars. For every star, there is a triangle. The triangles represent those indirect upper limits. So it's good, okay, it's good when the stars are below the triangles. It means that we've learned something new. And when that happens, there are these lines. And you can see, for example, here at 20, 30, 40, 50, 60, here, yeah. Here's the crab. This is the object for which the triangle is most far from our observation. This is because basically we're setting upper limits that are about a factor of 80, nearly 100 lower than the indirect limit. But for most objects, unfortunately, our observations are not informative. Now, remember, the gravitational wave amplitude depends on the deformation. So if you know the frequency and distance, which for known objects you do know, you can recast the upper limit on the amplitude as an upper limit on the ellipticity. And this is what's shown here, again, as a function of gravitational wave frequency. Here are the ellipticities for all the objects that were targeted. Forget about these lines. And so here I show this because what I get from this is that at the beginning you might think these are very impressive numbers, where 10 to the minus 7, even 10 to the minus 8 range ellipticity. And remember, I said, the ellipticity can vary a lot, but can be as high as 10 to the minus 3, 10 to the minus 4. 10 to the minus 5 is a perfectly reasonable number. And here we're probing even 10 to the minus 8. But for this population, actually, most but one of our upper limits are not very informative, okay? Because they are above the indirect ones. Where does this not happen? It happens here for these actually younger objects spinning down more fast, but at ellipticities that are actually not very interesting because they're really, really high, okay? So this is the reason why I personally think that it's more interesting to turn to blind surveys where you don't actually target known objects, okay, where you already know what the indirect upper limit is. But you hope that there's so many neutron stars in the galaxy, one that's just close enough and bumpy enough and spinning at the right frequency that we might be able to detect a signal. We're just not seeing it electromagnetically. Electromagnetically, we see 1,000 of these objects, 2,000, all right, 2,500. But there's 100 million of them. And so I'm very excited about actually broad all-sky surveys. Now, the problem is, since you don't know what you're targeting, you have to basically assume a source position, spin down rate. You do basically the computation of your detection statistic, and then you go to the next step and repeat. But, you know, we wanted really long observation to increase the signal-to-noise ratio. What happens when you increase the observation timeline, you also increase the resolution in parameter space. And basically, if you do up to first order spin-down search, the number of templates grows very quickly with your observation time. And since we're looking at observations that are months long, this becomes a completely intractable problem. You cannot do a perfectly coherent, so that would be the highest sensitivity search over months of data. Okay, so what we do is that we resort to different schemes. These are so-called semi-coherent searches, where instead of looking coherently at the entire data set, we actually chop it up in chunks. We do the really expensive search on each chunk separately. Okay, this is how we save computing time. And then we combine the results from the different chunks. Now, there's many ways of doing this. The way that I will illustrate is that this is basically this axis. Imagine it as parameter space. Okay, and so we compute coherent detection statistic per segment at all points in parameter space. And then how do we combine it? We just sum the detection statistic at 1 point per segment, okay? And so we basically have an average value of the detection statistic over all segments. And how do we pick the segments? I said how do I pick the point in parameter space in each segment? Well, basically, the detection set here is computed using a template grid that has a certain coarseness. This is this big white grid, okay? And how coarse it is depends on the time baseline that the segments cover, okay? So you can understand intuitively, and this is all, I'm trying to tell you a story, so I'm trying to give you the intuitive idea, right? That when you combine information over now a much longer time baseline, because you're looking at the entire set of segments, okay, the resolution increases. So you're basically able to distinguish points in between the big white cells. And so depending on what point I want to target here, this defines a summing track in this space, right? That's again, it's the idea. But actually, we don't do this just once. We don't choose a segmentation and do this and we're done. What we do is we do a whole hierarchy of semi-coherent searches, okay? Where at each step, basically, the length of the coherent observations. And the way we do it is that if this was an original set of waveforms, so the entire sky, a large frequency band, a large spin-down band, in the first search, we identify points that are interesting, that are high, and only on these we do a search that's now a bit more expensive because the coherent time baseline is increased, but it's also more sensitive, okay? And on the ones that survive these steps, we subject them to a search that, again, more sensitive, and so on, until we're actually on just a set of really interesting points, we do a fully coherent, super expensive per template point search. So you can think of it as this is your parameter space. At the beginning, I set a pretty loose threshold. Actually, there's a signal in here, but you see, it's a low threshold in the sense that noise fluctuations, will pass this. And it has to be, though, low enough that something that would be significant in the end passes. And here you can't see it. This is a color-coded projection of this plane. What happens at the second step? Well, now you get rid of more noise, but your signal starts showing up, so on and so forth. Another yes, absolutely. I can. Yes, the actual search, the coherent search, is a multi-detector search because you don't really care where the data comes from as long as you know its time tag and what detector produced it, so how it would couple to that specific signal. You just add all the data merrily together. Now here I wanted to illustrate, so noise rejection is the thing I was trying to illustrate with the previous slide. Another thing is that the parameter uncertainty decreases, right, at each stage because of this, because of the fact that the coherent time baseline actually decreases. So whereas here my parameter space in the uncertainty associated with every point was a certain size, at the end here it's much, much smaller. Okay, so from the point of view of a signal, this is basically a zoom-in procedure, okay? There's a number of ways to do these semi-coherent searches that produce different, that basically encode different trade-offs. And the trade-offs are basically these three pillars. Depth of the search, meaning sensitivity, breadth, how broad you search in parameter space, how broad, for example, a spin-down range you consider, how broad a frequency range you consider, versus also the robustness. And this is very important because this scheme here, allows you to, in the end, basically achieve the same sensitivity if you do not get rid of your signal up here that you would have if you could have done a completely coherent search. But at every step here, you ask for the signal to maintain perfect phase coherence. So here, you do get the maximum sensitivity at a cost. If for some reason your signal is not completely phase coherent, you will lose it. So obviously, there's other searches that you can carry out in order to be more robust, okay? But then typically you lose in sensitivity. I'm going to illustrate an example. This search is a search that my group we've carried out on open data, and it's a search where the trade-off that we made was that we were going to try and go as deep as possible. Yes, we were going to make assumption that the signal is completely phase coherent. After all, it wasn't such a long observing time, and I'll show you what that entails. So this was a really multi-stage search. Each line of this is one semi-coherent search. And this shows how the coherent time baseline increased. We actually used two data sets, the O3A, so-called, and O3B. These were released at different times. We didn't want to wait. And so we started off as soon as the O3A data set that was 6 months was released, we got going. And it was actually good because you want to have, if there's something that survives, you do want to have an independent data set to confirm it. And this is why we kept the O3B. We set it aside. We didn't use it immediately. Interestingly here, you can see this is the number of templates of waveforms that we searched. It's nearly 10 to the 19. So even this simplified, semi-coherent first search doesn't search 10 to the 28 waveforms, but 10 to the 19 is quite a big set, okay? And of these, we actually followed up only 3.5 million, which I believe, though, is a record. Nobody ever followed up this many candidates before. And the next thing I'm going to show you is, let me go back. Okay. All right, so 3.5 million were followed up, then nearly 400,000, 35,000. You see how they decrease. So we finished with the O3A data set, and we have 12 candidates left. Oh, cool. Could be that they're signals. So we took a brand new data set, the O3B, and followed up all of 12. And we were left with 6. And then we put together the O3A and O3B set and saw, now demanded coherence across this longer data set and survived all 6 of them. All right, and we were very excited, but LIGO does hardware injections. So injects fake signals into the data, continuous wave signals, to provide basically a test as up in the food chain, in the chain of all the operations that need to be carried out, to provide the most complete end-to-end testing. And the 6 candidates that survived were all hardware injections. So they were all fake signals actually inserted in the data for validation purposes. And what I want to show you is the accuracy, and these are shown in these 3 columns, in frequency, frequency derivative, and sky, that we could recover these with. And so this is basically the, that's the promise of long baseline observations. These type of accuracies you're never going to get with the binary in spirals, okay? These are the upper limits, meaning it's the red curve, okay? And what you see here are the hardware injections, meaning it's the amplitude of the hardware injections. Obviously, we recovered all the ones that were above our sensitivity curve, but we also recovered a few that were below, and this is because these had more favorable orientations, okay? Her limits are to be intended across all possible polarization states. So they're 90% confidence upper limits. So most orientations that will actually are favorable, and we will be able to detect them even with amplitudes lower than our sensitivity. These are in gray the results from the official LIGO Virgo results, where, truth be told, they appear to be less sensitive. They are, but they looked at a slightly larger range in spin down, okay? And here you see 8 times to the minus 26. Don't know if you can remember, but the number for the known pulsars was like 3 times 10 to the minus 27. So it was significantly lower. This shows how you kind of lose sensitivity when you look at such a broad parameter space. Translated in, yeah. Right, yes, thank you for. This is actually the one injection that we missed. We didn't recover these. So you see, these are 1, 2, 3, 4, 5, 6. But there was one here that we missed. So, okay, you could say, well, all right, it's slightly below your curve, your sensitivity curve, so it's okay. And yes, it's okay. But the reason why we missed this one is that the parameters of these just happen to be at a very unlucky point in parameter space. We set up grids, and our ability to detect signals in between parameter grid points varies. And this was just right in the middle. It was a really unlucky one. Okay, so those upper limits, translated in upper limits on the source ellipticity, now need to be parametrized by the distance, because unlike for known sources, we don't know where the source is at what distance. So we say here, for example, if we concentrate on the orange curve, we would say, what does this point mean? It means that we can exclude that the ellipticity of any object within 1 kiloparsec and rotating faster than 300 hertz is above 9 times 10 to the minus 7. Okay? And so these, again, if you remember, sort of indicative plots, indicative numbers at the beginning about the ellipticities of objects, show you that we are probing a physically plausible parameter space. Now, the first stage of the search is where I search the entire parameter space. That's when I basically search 10 to the 19 templates. That's very computationally expensive. And the sensitivity, the ultimate sensitivity of the search depends on that, okay, and where I put the threshold. And so for that, we use a volunteer computing project that we set up back in 2005 called Stand at Home, that basically leverages the good heart of people who donate their idle compute cycles for the advancement of science. And this basically provides tens of thousands of machines 24/7. Actually, this number is a bit smaller if we use GPUs from the machines. But please consider signing up and providing, helping us do these searches. The search whose results I just showed you took 6 months, 24/7 on Einstein at Home. So it's really important. By the way, Einstein at Home also looks for pulsars in radio and gamma and X-ray data, and has found, using the sort of techniques that we developed for continuous waves, a lot of pulsars. The successive stages are also intensive, and for those we use the in-house computing cluster that we have in Hanover. All right, what are the chances of detection? I don't have time to go into this, but basically the chances of detection have to do with the chances to have an object that's spinning at the frequency that's right in the LIGO band, okay? And whether that happens or not depends on how the spin frequency of this object evolved over its age, so it depends on its age, and over how the object lost rotational energy. And that depends on its ellipticity and on its magnetic field. Of course, the amplitude of the signal also depends on the ellipticity and on the distance. And then there is the position of the object, and this depends on where it was born and what kick velocity it has. Then our ability to detect it depends on the search setup, but also depends on the noise of the detector at the frequency of the object. So it's hard to predict, and I would like simply to point you to this paper that we put out last year, the first in the audience here, Gianluca, and we basically tried to convolve together all the effects for at least a population of non-recycled neutron star. We started with the simplest sort of problem, and then analyzed the sort of the detectability, the chances of detection. So we consider different models because all these parameters, we don't know them. We don't even know the distributions. And we consider different models, not because we believe that each single model could be the right one, but mostly to get a sense of the spread of answers. And so this is the expected average number of detectable signals right now, okay, depending on the models. And here is to say that for a lot of models, the situation looks quite bleak, basically chances at the order of percentages. But there are some models that predict a few detections, although with a large uncertainty, okay, which is consistent with the fact that we haven't detected anything, okay? We would be surprised it would mean that our models are grossly wrong if, I told you to expect 100 detections. But the good news that I am going to give you is that with the next generation of detectors, the Einstein telescope and Cosmic Explorer, we do expect from some model a significant number of detections, which conversely means that if we do not detect anything, we might actually learn something, could infer something about the population of objects out there. The ingredients in the different models are basically the distributions of spin frequencies at birth, okay? Distributions of magnetic fields and of ellipticities. It's a uniform distribution between, let's say, 10 to the minus 14 and a maximum which could be either determined perhaps by, with 10 to, yes, okay? And there's different, we take different models, log uniform. Okay, I don't want to spend a lot of time on this, but since I spent my entire talk here talking about neutron stars, I just wanted to put this little voice in your head when you think back at continuous waves, that actually there's other signals, the ones that I said, and if the signal was not from a neutron star, it would be even more exciting. Okay, there's other scenarios where we would get basically the same kind of signal that these searches could pick up, not coming at all from a neutron star. And here we have Masha in the audience, who is the expert on this sort of scenarios where basically boson annihilations following the formation of gravitationally bound states of ultralight bosons around black holes will source continuous gravitational waves. So this means that we could actually interpret the upper limits on gravitational wave amplitude in upper limits on the boson mass, and this actually has been done assuming scalar bosons. And here is a plot from a paper back in 2020, where we actually again simulated ensemble signals that we would expect from a population of galactic black holes, the 10 to the 8 isolated galactic black holes. We considered distributions of the black hole masses, of the initial spins of the black holes, and each of these sort of a population would give rise to a different boson cloud signal as a function of the boson mass. And we counted the ones that would have been detectable. And you can see basically that unless here you consider a really initially very slow spinning black holes, we would have expected to have detected signals from this, from boson masses that go from about 5 times 10 to the minus 13 to, probably a few 10 to the minus 12. And so the fact that we haven't actually is a direct probe of the fact that these signals are not there. And there's a lot of caveats on the assumptions that went into the signal description that we use, self-interaction, the fact that we only considered the first modes. You can read the paper, but this was really to tell you that there's a broader class of signals than the ones coming from neutron stars that these sort of searches probe. All right, I'm going to finish though with something, but it's important to me because this is something we're not doing well. Most pulsars in ground-based detectors, meaning in the frequency band of ground-based detectors, are in binaries. So for example, if you plotted the frequency and spin down in gravitational wave expected from known pulsars from the ATNF catalog, you will see that above 10 hertz, which is above 20 hertz gravitational wave frequency, more than 50% of pulsars are in binaries, which are the red ones here. And so far, I told you about searches, broad surveys for objects that are isolated. The problem when you try and look for objects in binaries that you don't know of is that not only do you not know where they are and how they're spinning, you don't also know the orbital parameters, which means that you add search parameters. So you add the different waveforms to already a problem that's computationally difficult. So these show the upper limits, the best upper limits that are now around 3 × 10⁻25. So you see the searches get, the more parameters you search over, the least sensitive the searches get. In the frequency range between about 50 and 500 hertz. This is what my group did in a paper published in 2022 to great expense, because going to higher frequency is more expensive. Searches at higher frequency, since the resolutions are scaled with frequency, they're much more expensive. And we search for objects. This is the search, my group's search in 2022, with orbital parameters in this range. And this is the parameter range chosen just a year before by the LIGO Virgo Khadra collaboration. So you see, similar, they're basically trying to follow the population of known pulsars. But the fact is that these plots here don't quite factor in the frequency. You see, if you look at the frequency of these objects, in the frequency range that was searched by LIGO, only 12% of these known binary systems fell. So we decided to go to high frequency that was very expensive, because at least we covered nearly half of them. So this is only to say that these are computationally expensive and difficult. You see the upper limits on the ellipticity here get worse. We can only exclude within 1 kiloparsec ellipticity greater than 3 × 10⁻⁶, again for objects spinning faster than 150 hertz. And the problem is that you have limited computation resources, so you have to make these trade-offs. So it's like your blanket is short, you pull it one side and you cover one bit, but the other one now is not covered. So I'm hoping there's students here that feel this is perhaps a place where new ideas, new clever methods can help. Neural networks, yeah, perhaps they could help. So far we haven't been we haven't had much success, because basically we're operating in this regime where the information is scattered in relatively large portions of a big parameter space, and they're very, very weak. Whereas here, deep convolutional networks operate in a completely different regime, kind of quite high SNR and localized, well-localized feature, and then they can hierarchically, zoom in, basically. So we're basically trying to understand what type of neural networks, sort of custom designed, can be built for this specific problem. And recently we've had some success, but baby steps. We can now basically construct a deep neural network that can match the maximum log likelihood detection statistic, which is the optimal, in the Neumann-Pearson sense, detection statistic, only with coherent times of 10 days. It's not bad, but we need to bridge, the really long time baselines. So there is really much work to do to do here. So I've come to the end. I hope I gave you an idea of what this type of research is, why it is important, why is it promising. There's a number of open problems, but I think it's a high risk and possibly high gain enterprise that would open a new window in the gravitational wave spectrum. We're looking at the transient sky right now. We would be looking at the constant hum in gravitational waves. That's different. The binary in spiral signals are allowing us to probe population of black holes, black hole evolution, tests of GR. And so you don't hear often talks about, continuous waves. But I was there, being so old, so I would like to remind you that, LIGO persevered through a lot of skepticism, okay? And it was only because people were willing to invest in something that, the payoff when it comes, it's so exciting that it's worth the risk, that we were able to achieve the breakthroughs that we see now. And so I hope that this applies also to continuous waves, and I hope that I've inspired some of you to perhaps look at this, because I think that the only guarantee for failure is if we stop trying looking for them. And with that, I'm done.
Thank you, Maria Alessandra. So I have a question. So in the very first part of your talk, you described like 2,500 pulsars. So I imagine this has been done. So if I assume a very simple model for each pulsar that is going to rotate at twice the frequency as far as the gravitational wave is concerned and the pulsar frequency, I can stack them all, but with a suitable mapping. So I could do a better, factor of 50 better.
It's been done.
And?
Yeah, and nothing.
Really nice talk, thank you. I wanted to ask about tidal effects when you have, for example, a neutron star and other compact object mergers, and whether this has any detectable signature in the transient and, maybe the few hours pre-transient event in the LIGO.
Mm-hmm. Well, those, tidal effects are certainly being investigated in the binary in spiral sort of searches, and these are very, very short lived ones, unfortunately. So not yet completely, characterized and seen. And for these, obviously, they're not in this category.
Good upper bounds have been placed. So the star radii would have been larger. There would have been modulations of waveforms which were not seen. And so that's how LIGO put bounds on the tidal effects, on the tidal of them.
And then from that also right on the equation of state.
Questions? Let's thank you again.